Hello, welcome. Today we will work on an indeterminately static example concerning the twisting of round bars. Let's get started. A bar with a variable diameter d and 2d, here we have diameter d, here is twice the diameter, is fixed at both ends and twisted by moments m0 and 3m0, as shown in the illustration below. Draw the twist moment graph, the maximum stress graph tau max, and calculate the angles phi k of twist of section k. We have given intervals of 1 meter each, this diameter, and moment m0 1000 nanometers, kn/mg equals sine 80 GPa. Let's start. Let's label the sections A, B, C, D to make calculations easier. The problem is statically indeterminate. We have one equation from static moments available, but two unknowns are present. This means the moment at one fixation and the moment at the other fixation. We have to utilize a geometric condition here. The geometric condition for this problem is that the total twist angle of this bar equals 0 because the bar is fixed on both sides. This doesn't mean that the bar isn't twisted at all. It just means we can write an equation indicating that the total twist angle equals 0, because it will be twisted at this section, but both at section A and section C, the angle equals 0. Now, based on this geometric condition, we determine the moment at either one fixation or the other. The choice is ours. It's indifferent. If we proceed from the left, making theoretical sections from the left, in the last section we reach infinitely close to section D, meaning we don't account for the moment at that fixation. We will do it this way. We could do the reverse, mark the moment at D, and proceed from the right side, not reaching the other end. It's all the same. Remember the notations. Positive twisting moments are moments whose direction points outward from the notional section, and negative ones point inward. Now we recall notation according to the right-hand rule. If we position our hand like the moment MA, the thumb shows us the moment is directed outward, meaning it's positive looking from the left. These moments are directed to the right. The geometric condition I mentioned is that the total angle of twist is 0. And the total angle of twist from the superposition method is the sum of the twist angles in these three sections. Remember the twist angle formula. Twisting moment times the section length. Kirchhoff module, moment of inertia for twisting, meaning we now list the twisting moments in our three sections AB, BC, and CD. Therefore, the twisting moment in section AB, we make a theoretical section from the left, something like this. And observe, here we only have moment MA. Therefore, this section, I symbolically drew it, is somewhere in section AB but infinitely close to point B, meaning we do not yet see the moment 3m0. We only see the moment MA, whose direction is outward, meaning it's a positive MA. And similarly, we move this imaginary section to this place, somewhere between points B and C, meaning we see, looking from the left side, now this moment 3m0, whose direction is towards the section, meaning it's negative. MA minus 3m0, and the moment in the CD section, which is up to the moment MA, actually from moment MA, we subtract 3m0, and then additionally subtract m0, and this is the moment in the CD section. In this formula, we also have the moment of inertia for torsion, so we glance at the table, whose link will be in the description of the video. And here we have a circular section, yes, which means torsional moment of inertia, circular section pi d to the 4th over 32. All right, let's go. The AB section and the BC section have the same torsional moment of inertia, because they have the same diameter. This diameter here is exactly 2d, meaning pi times 2d to the 4th over 32 reduces to this form. CD section, the diameter is d. And as I said in the BC section, the torsional moment of inertia is the same as the AB section, but in the CD section, it's pi d to the 4th over 32. For now, I'm not substituting this value, assuming d is given as 5 centimeters, but to calculate the moment in the fixed part for now, it might even be better if we don't substitute the values. Because firstly, we will get a more accurate result. Well, let's leave it at that, and secondly, it will be easier. And precisely to make it easier, let's make a ratio of the moments of inertia AB to CD, or the other way around CD to AB, it doesn't matter. I did AB to CD, meaning the moment of inertia for AB is pi d to the 4th over 2. We divide it by the moment of inertia for CD, and we will see what the ratio of these two moments of inertia is. Dividing by a fraction means multiplying by its reciprocal, meaning pi d to the fourth cancels out and we get a neat 16. By multiplying by the moment of inertia for CD, it follows that the moment of inertia for AB is equal to 16 times the moment of inertia for CD. And now for the equation for the angle of twist. Instead of substituting the moment of inertia for AB, I will write 16 moments of inertia for CD. Instead of substituting BC, it's the same as AB, meaning also 16 in CD. And that's what's happening here. Torsional moments for the subsequent sections are listed here, meaning AB is MA. Moment of inertia, torsional moment BC. We've written CD, we've written the lengths of the sections L. For each section that is LLL, meaning per meter. But this will soon be simplified. And the Kirchhoff's model is constant. It could be different if it was clearly stated in the task content that, for example, the rod is made of different materials, like steel and copper. But we don't have anything like that written here, so G is the same for all three sections. So what I said, the moment of inertia AB, moment of inertia BC, and moment of inertia CD is simply ICD. So now we have a common denominator G and CD. On the right side, it's 0. If we multiply by G and CD, it will cancel out. If we divide by L, it will cancel out. That's what we are doing. Here is IBC, it should be ICD, of course. So what do we have left then? Then 1/16 MA from the first. We have 1/16 MA minus 3/16 M0 plus MA minus 4 M0 left. That's exactly how it is. We sum MA and M0 to the right side. We are left with, we multiply by the reciprocal of what's with MA, 67/18 M0 left. In a fraction 3.72 times M0, meaning M0 was Kn times meter. So that will be simply 3.72 Knm. So now we are able to draw the torque diagram. Now we move on to shear stress. Shear stress is the torque divided by the torsional strength indicator. The torques in the respective sections are already listed. We take the torsional strength indicator from the same table I showed earlier, and it's pi d cubed over 16. So in section AB and BC, it will again be the same strength indicator since the diameter is the same, and our diameter is actually 2d. So here we already substitute values to have specific shear stress values. So I substitute 2 times 5 centimeters, 10 centimeters, convert to meters to have base units. The result is in meters cubed. We have the strength indicator for BC the same as for AB. And now CD, I substitute 5 centimeters. We have the result in meters cubed. So we calculate the shear stress. The shear stress in section AB. So the moment in section AB, which is MA, which is 3.72 Knm, or times 10 to the power of 3, divided by the strength indicator in the base unit. And if you put such a formula into a calculator, the result is in the base unit, which is in Pa. To get MPa, we must multiply by 10 to the power of minus 6. We do the same for section BC. And for a moment, we must say goodbye to the panda. We do the same for section CD. And here, if there's a negative torque, the shear stresses are also negative. I hope this is clear. We have left to calculate the angle of twist. And in the previous video, meaning so far we counted this without the integral. In the last video I mentioned that it can be calculated with an integral. It will be necessary if we have a continuous applied moment, meaning not concentrated as we have here, but a continuous twisting moment load over a length of the interval. And generally, we can either use a definite integral that is within the limits of integration. If we wanted to calculate it at a specific point, say at the midpoint of the interval AB, we need to do the integral from the start to half L. And we can calculate it just as well without the limits of integration, that is an indefinite integral. Then, as a result, we get a function of this variable depending on the length of the bar we want to calculate the angle of twist. Then, by plugging into this function any value based on the length we are working with, if we write the function over interval AB, by plugging in any value from interval AB from 0 to L, we calculate the angle of twist at any point. And here in this formula is the torsional moment of inertia. We need to calculate it because on the previous slide, we only did the ratio using symbols. And here we substitute actual values on interval AB. It is the same on interval BC, so there's no need to write it. And on interval CD possibly. Well, not possibly, we will also calculate it. And now we can write the indefinite integral, the moment of twist from 0.72 times 10 to 3. Kirchhoff's modulus in the denominator and the torsional moment of inertia, which we calculated here, these are constants. This entire fraction is a constant. We take it out of the integral and have an integral of dx. The result of the integral of dx is x, and it is in radians per meter, and substituting any bar length in meters, that is, any value from 0 to L, because this is the angle of twist in interval AB, any value in meters over interval AB we calculate, then the meters cancel out the angle of twist in radians. And we do the same on interval BC, substituting the twisting moment instead of the previous slide, Kirchhoff's modulus 9.82, the same torsional moment of inertia, and the constant outside the integral of dx is x. And now the angle of twist at section A is 0. The angle of twist at section B is from the method of superposition. The angle of twist at section A plus the angle of twist in interval AB for the whole length, that is for L, that is for 1. So we substitute 4.74 here and multiply by 1. Nothing changes, just the meters cancel. And the angle of twist at section C is the angle of twist at section B plus the angle of twist of this BC interval. This BC interval, here it is a variable, so the angle of twist in the BC interval at the end, which is at 1 meter. And now I wanted to show you that in some tasks we have, for example, a certain condition. Geometrically, let's say the allowable angle of twist is a certain amount and is given in degrees. You must be able to convert it, let's say, to degrees or vice versa. Here we will draw a graph in degrees, so let's convert it to degrees. To convert to degrees, we multiply by 180 over pi, and the result is in degrees. We can better imagine what order of magnitudes we are talking about. Because 4.74 radians, does anyone actually know how much that is? I, for example, don't really. But 27 degrees, well, that's more understandable. All right, as I said, twist angle at cross-section C. In the task content, they asked about the twist angle at cross-section K because it's marked here, but it's the same thing. Well, as I said, we add the result from phi BC, multiplied by 1 to these 0.27 degrees. And we multiply immediately by 180 over pi to convert to degrees. We have 0.32 degrees. And here, I didn't write the CD twist angle further, because this is where we could eventually check if it goes down to 0. The sum should eventually be exactly 0. But to shorten this a bit, I know that from point C to point D, from C to D, I just have to go down to 0. Because the rod is anchored from both sides. Well, shear stresses were calculated on the previous slide, and we draw graphs, meaning we had functions MEB, MBC, MCD. I just insert the values. Here is the step graph. It would be linear if there was a continuous twisting moment load. Now about shear stresses, also a step graph. I just insert the values. There's nothing complicated here. And the graph of the twist angle, it is always 1 degree higher in equation than the twisting moment graph. So if here is a constant value, the twist angle is a linear function. That's why I knew here how from that twist angle at C to 0 linearly, there's no other possibility. So here we know it's 0. Here we know it's 0. Here we know it's 0.27, Here are 0.32, / graph drawn. And that's about it for this example. Thanks for watching. If anything was unclear, or you have any questions, feel free to ask them under the video. Visit our Facebook profile, like us, and you'll stay updated with what's happening on our end. On our website, you'll find many useful examples nicely described. Of course, subscribe to us to receive fresh updates about new videos. In the meantime, take care, bye.